This chapter of the book is on an introduction to differential equations. In fact, it could be part of the last chapter, applications of derivatives, but it seems like kind of a different sort of problem. So these things are in a different chapter. In this first section on what is a differential equation, I just want to discuss what a differential equation is and what it means to solve it, and what a unique solution means, and kind of the problem of when you may not have one, and the fact that solutions may only exist near some initial data. So that all of these kinds of questions about what is a differential equation. And then I thought I'd give an example of kind of a fairly complicated but at the same time fairly easy problem where it's a physical problem in terms of rates of change. And it's once you have a problem that's described in terms of rates of change, a rate of change is a derivative, so you have an equation with a derivative in it, and so you tend to get differential equations. All right, so what is a differential equation? Well, I mean, the easiest thing to say is it's an equation with a derivative in it. So let's look at dA dt equals, I want t times a squared. Let's look at this. This is an example of a differential equation. What does it mean? It means that A is, or what does the solution to it mean? It means that A is some differentiable function, A, which should be a function of t, is a differentiable function which satisfies this equation. So a differential equation is an equality of functions. So in this example, functions of t. This is an equality of functions of t. A solution to this, what we're saying, what a solution is, what this says is that A is a function of t such that dA dt, so the derivative of A with respect to t, which is another function of t, always equals this function of t. What function of t is this? The one you get by taking that A and squaring it, multiplying times a t. This is what a differential equation is. It's an equation involving derivatives, and it's an equality of functions, at least for all times in some open interval. It's an equality of functions, and a solution to the differential equation is to explicitly give the function, or even sometimes implicitly give the function, if you can't solve some of the algebra, but you can get rid of the derivatives. So later, in the third section, we'll actually be able to solve this differential equation. But right now, I want to say that solving it means finding all of the A's that make this true. Right now, I can tell you all of the A's that make this true. There's the function A that's always 0, and there's the function A that is 2 divided by 2 over c minus t squared, where c is any constant. So I claim that this represents all of the solutions to this differential equation, at least solutions defined on intervals. This, as you can imagine, as you know, if t squared were to equal c, so c is some positive number, like even 0, but suppose c were 2, then when t is plus or minus the square root of 2, the denominator would hit 0. So this function is not defined every place. Typically, we look for solutions to differential equations on intervals. So, so these are all, let me back up a little bit. This is all the solutions. At least defined on intervals. This collection of all the solutions is just referred to in the singular as the general solution to the differential equation. So the general solution is actually an entire collection of solutions. It will typically have some arbitrary constant in it somewhere. Sometimes you have special cases like this one. And seriously, we only necessarily expect to have solutions defined on intervals. And if you have solutions defined on two different intervals, you can frequently patch those together and make a new solution that looks like one of them on one interval and another one on the other interval. So when we talk about the general solution, we mean functions defined on intervals. What does it mean to say that these are solutions to this? It means if you stick those functions in here for A, that this differential equation is satisfied. So it's never supposed to be an issue to verify that something is a solution to a differential equation. Producing the solutions, that's something else. But verifying that some things that you're handed are solutions is easy. So here's our differential equation. Y is A equals the constant function 0, a solution. Well, it means that when you put 0 in over here, you get what you get. When you put in A equals 0 over here, you get the same thing you get when you put in A equals 0 over here. Well, if A is the 0 function, its derivative is 0. So certainly dA dt is 0. But that's certainly the same as t times 0 squared. Right? Both of these are 0. So dA dt equals t times a squared because they're both 0. Well, that case is really easy. The other case is you actually have to do more work. So why is this a solution? So y is no matter what the constant c is. Well, we can just do it. So it's nicer to write this is a equals 2 times c minus t squared to the minus 1. And then what do we have to do? You calculate dA dt. You calculate t times a squared, and you verify that they're the same. So dA dt. All right, 2 is a constant. Here you do the power rule. Subtract 1 from the exponent. But then by the chain rule, you have to multiply times the derivative of the inside stuff. So you have to multiply times the derivative of c minus t squared. The derivative of c is 0. Derivative of negative t squared minus 2t. So what we get, there's a minus and a minus. So that's a plus 4t. And then this is divided, so we get a 4t over c minus t squared, quantity squared. Okay? That's dA dt. What is t times a squared? If a is this, you get it is t times 2 over c minus t squared squared. But when you square a fraction, it's the same as squaring the numerator and squaring the denominator. So we get a 4, and then times a t, and then over c minus t squared squared. Look, they're the same. Yes, yes, dA dt equals at squared for these too. So yes, all of those things are solution. A equals 0, a is the constant function 0, a is 2 over c minus t squared. How do we know those are all the solutions, at least on intervals? We have to learn how to solve differential equations. This one is easy. It's called a separable equation. We'll look at those in a couple of more sections. But right now, let's just believe that these are all the solutions. They are on intervals. So these are all the solutions to this differential equation. And I'll say it again, this collection of solutions is referred to as the general solution to the differential equation. All right. Frequently, you don't just want one solution. Let's try that again. Frequently, you don't want a whole collection of solutions. You want just one. But of course, they're an infinite number. But you're frequently given initial data. So instead of just being given this differential equation, maybe you're told the value of the function a at some t value. So I'm just going to use variables, but assume that at some particular, I'm thinking of t as time, at some particular time, t naught, you're told the value of a is some particular number, a naught. Now this is called an initial value problem. It's a differential equation together with some data that we call initial data. Frequently t naught is 0, so it really is data at times, and frequently the independent variable is time. So you're frequently given data at time 0 in physical experiments, in physical situations. You frequently say, all right, our situation starts now. I'm calling this time 0. I know this value at time 0, and then this differential equation has to be satisfied. So for that reason, it could be reasonably called initial data because it's data at time 0. Even if the independent variable is not time, even if the given value of the independent variable is not 0, we tend to call this given data initial data, and you should think of it as just data that you're given initially. It's an initial value problem. This, by the way, I should have said this. This kind of differential equation, this is called a first order differential equation. It just means the order is the highest power of the derivative you see in the differential equation. And in this introductory chapter on differential equations, we're only going to look at first order equations. So that means only the first derivative is involved. dA dt or dy dx or something. Only first derivatives, no second derivatives, no third derivatives. Okay, so just more terminology. Okay, yeah, you start with a differential equation. General solution means what the collection of all solutions to the differential equation, at least defined on intervals. An initial value problem, a differential equation together with some given data at a particular value of the independent variable. You know that the function has some given value. Such a differential equation is called a first order equation if the highest power, or the highest derivative that you see is the first derivative. All right, what do we want? We don't want the general solution. Now we'd like to know if giving t naught and a naught, so giving the initial data, does that isolate one of these solutions for us so that instead of a general solution, we want one particular solution. And that term, particular solution, is a real mathematical term. Can we find, it just means a specific one as opposed to the general solution. Can we find one particular solution to the initial value problem? And actually, this is phrased very poorly, and I'm going to change it. But we'd like to find a solution. So amongst all of these solutions, which I'm telling you is these are compose the general solution. So every solution looks like this on an interval. Can we find one that satisfies the initial data? All right, we'll see that we can. But that isn't really what we mean, when you want to find one particular solution. We mean, is there only one? So it's not, can you find one? Because that doesn't, maybe there's still another one. So can we find one solution to the initial value problem? And what we really mean is, and show that it's unique. It's the only solution to the initial value problem. We like for solutions to be unique. We don't just want to find a solution that works. Yes, a particular solution just means some solution as opposed to a collection. But we'd like to know that it's the only solution. Why? Because the way you use differential equations, and they come up in all kinds of physics and engineering applications, is for physics reasons or for lots of reasons, you get a differential equation because you know something about rates of change in the problem, like we're going to do an example of rates of change in a mixture problem. Sometimes it comes from big physics, like differential equations come from big physics principles. In fact, they frequently do. But other times it's just some reasoning and you're given data about rates of change. In any case, you're usually given the physical situation, or when differential equations come up, gives you rates of change information. And what you'd like to know is, given this information about rates of change that you translate into a differential equation, so you model the situation with a differential equation, and given the initial state of things, so given the initial data, you would like to be able to say that this one thing will then happen. Well, that means there should be a unique solution to the initial value problem. You don't want some kind of uncertainty principle in solutions to your differential equation that if I have this differential equation and I start with this data, maybe this happens or maybe this happens. We don't want that. In physical applications, you typically want to know that if you've got an initial value problem describing your physical situation, that there's a unique solution, at least for a little while, for some time interval around your initial time. You'd like to know that the solution is unique if your independent variable is time. All right, so let's see. If we fix that the value of A has to be A naught when T is some particular T value T naught, does that tell us that we get one of these solutions and only one? So is there a unique solution to this initial value problem? And the answer is yes. So, all right, let's do this problem. So we know what all the solutions look like. You're just going to, in this section, you just have to believe that all the solutions are of this form. And now we're given A at T naught equals A naught. And we'd like to say that that isolates one of these solutions for us. Well, first of all, if A naught is 0, so there are cases. Case 1, what if this A naught that we're given is 0? Well, if that's 0, then this solution satisfies the initial data, because it's always 0. And in fact, it's the only one, because this is never 0. It's a quotient. This is never 0. Case 1, if A naught is 0, the unique solution to the initial value problem. Is the function that's always 0. Okay. What about the other case? Case 2. A0 is not 0. So if A0 is not 0, presumably we get one of these other functions. But let's see that knowing T0 and A0, the whole question is, does it tell us exactly what this C is? Well, first of all, does there exist a C that works no matter what we pick for T0 and A0, as long as A0 is not 0? And is there only one? So what do you get? Well, we would need, so we want this initial data to be satisfied, which means that we would need for A0, so when you put in T as T0, you should put in A as A0, you would get A0 equals 2 over C minus T0 squared. And we'd like to know that there is a C that makes this true and that there's only one. Well, multiply both sides by C minus T0 squared. Right. Divide by A0, which we can do because A0 is not 0. So we get C minus T0 squared is 2 over A0. And then add T0 squared to both sides. So yes, there is a C, a constant C that we could pick that will make something of this form satisfy the initial condition. And there's only one. Given A0 and T0, this is the only one. So the only solution, we still are believing these are all the solutions, is that A is 2 over A0 plus T0 squared minus T squared. This. So, yeah, if you specify initial data in this problem, there's a unique solution. So yes, when you just have the differential equation, we just have this differential equation, no, you can't expect a unique solution. And it has to do with the fact that you kind of undo differentiation and get a constant that vanishes when you differentiate. It produces these constants in the general solution. So when you have a differential equation like this, yeah, you expect a general solution like this with an arbitrary constant in it. But once you're given some initial data, you at least have a hope that you get a unique solution. It's possible that that fails, and we're going to look at an example of that next, but you can hope that there's a unique solution, as in this problem. Let me, before we leave this problem, I want to look at one more thing. So we had, what we just found is that if our initial data, that there were two cases. If A0 is 0, the solution was A is the constant function 0. If A0 was not 0, we found that the general solution was was 2 over A0 plus T0 squared minus T squared. Now, first of all, this is aesthetically unpleasing, this fraction in the denominator of this fraction. Secondly, it's kind of cool what happens if you make that look better. So I'm going to multiply the big numerator and denominator by an A0 to get rid of this division by A0. So we're in the case where A0 is not 0, so we can do that. In the numerator, then, we would get 2A0. And in the denominator, you get 2 over A0 times A0. That's 2. And then you get plus a naught times this quantity, which I'll leave that way, as t naught squared minus t squared. All right, so great. You know, I think that looks more aesthetically pleasing, but you know, beauty is in the eye of the beholder, but I like that better. What's another nice thing about it? Oh, it includes this case, because when a naught is 0, the denominator would be 2, the numerator be 0, and we would get the 0 solution, which means if you write the solution in this form, you don't need to have two separate cases. That this one way of writing the solution includes the two possible cases where a naught is 0 and where it's not. So this is, in some sense, or in a strong sense, the nicest way to write the solution to this initial value problem. And in fact, okay, it's the solution to the initial value problem, but it's also, in a sense, the general solution, because we did this for no matter what the initial data is. All right, the last thing that I should say about this problem is, I'll say it again, that this solution is not necessarily defined for all t, right? If the denominator hits 0, then this solution is undefined, and that can happen, right? It's, if you look at it before we messed it up, before we beautified it, if you look at it in this form, the denominator would hit 0 if t squared, we have a problem, so a is undefined, if t squared equals 2a naught plus t naught squared. So that would be when t is plus or minus the square root of t over a naught plus t naught squared. If this is actually a positive or non-negative real number, then there are actually times when you'd actually get t's for which this is undefined. On the other hand, if 2 over a naught is negative, and so that, and big enough, or negatively big enough, so that it overwhelms the t naught squared, so that this is negative, then t squared equals a negative number. That wouldn't happen for any real numbers t, and so the solution would be defined every place. But for some initial data, your solution is only defined on an interval containing t naught, and that is what you expect, that we only care this solution may be, depending on the initial data, only on an open interval containing t naught. And this is typical in differential equations, that for some differential equations, you can only hope to produce a solution that's defined on an open interval surrounding your the initial value of your independent variable, so here t naught. Yes, ideally you would like to extend that solution and say, oh, and in fact it's the only solution for the rest of time. And sometimes you can do that, and sometimes you can't. But in general, we only expect to find solutions that are defined near the initial values. Okay, I finished beating on this problem. I'd like to give an example of a problem of a differential equation that does not have a unique solution. even near the initial data for some values of the initial data, just to show you that bad things can happen. So in that last problem, we saw that if initial data is specified, you can produce a unique solution near your initial value of the independent variable. However, that's not always the case. So here's another example. Another example, consider dy dx equals y to the 2/3 power, and y when x is 0, y is 0. I'm just going to, once again, I'm not trying to tell you how to solve differential equations in this one, but I'm going to say that we'll verify that there are two different solutions to this initial value problem near where x is 0. Verify it. So actually they're globally defined. They're defined everywhere. Verify that y equals y of x equals 0 and y equals x cubed over 27 are solutions to this initial value problem. All right. Before I do that, let me point out why we care. I said it before, I want to say it again. If this were describing some physical situation, so for some reason you knew for physical reasons that the rate of change of y with respect to x is y to the 2/3, and when x is 0, y is 0, and then you want to know, okay, what is y when x is 5? Well, too bad. You're not going to know because there are two different solutions to this. And it's just physically, this would be ill-posed. It would mean you had modeled the situation poorly. You were trying to write down some mathematics that would tell you exactly what would happen, and instead you got two choices. So you need to describe your physical problem some other way. Why are these both solutions? You can just check. Is this a solution to this differential equation? Well, if y is the 0 function, its derivative is 0, and 0 to the 2/3 is 0, so certainly this satisfies the differential equation. When x is 0, is y 0? Well, y is always 0. So yes, y equals 0 is certainly a solution to this initial value problem. What about y equals x cubed over 27? Well, we have to check. So suppose y is x cubed over 27. Then dy dx. The derivative of y with respect to x is 3x squared over 27. That's x squared over 9. What's y to the 2/3 if y is this? Well, y to the 2/3 is x cubed over 27 to the 2/3. You take the cube root and you square. The cube root of x cubed is x squared. You get x squared. The cube root of 27 is 3. 3 squared, 9. Yes, this is x squared over 9. Yes, these are equal. So this is a solution to the differential equation. And when x is 0, y is 0 again. So yes, it's a solution to the initial value problem. These are two different solutions to the same initial value problem. We wouldn't mind if they were the same near x equals 0, that if there was only one near x equals 0, but you could mess up the solutions far away from x equals 0, we wouldn't mind so much. But in fact, these are both defined near x equals 0, and they're not the same near x equals 0. So this is bad. We have a non-unique solution. So solutions are not unique. In fact, using the plural means they're not unique. Solutions are not unique. Even near x equals 0. That's a problem. So in general, we don't want that kind of thing. All right. While I'm on non-uniqueness, let me go back to this first example that we looked at. So in the first example, one of our solutions, whether you write it with t naughts and a naughts in it or not, we could get this for a solution to the initial value problem. So suppose we have an initial value problem and we gave ourselves some initial data in that first example, and this is what we get for the solution. As you can see, this will be undefined when t is, so what initial data would give us this? Well, you can do it after you've written the solution. When t is 0, a would be a half. So we're assuming we had this differential equation, dA dt equals t times a squared, and this initial data. And then the unique solution is this. You can redo that from what we did before, or just know that this is 2 over c minus t squared, and in fact, when t is 0, a is a half. Okay. Yes, where is this defined? It is not defined when the denominator is 0, so when t is plus or minus 2. So we get a solution. So here's minus 2. Here's 2. Here's 0, our initial t value. And we get a solution in this interval containing 0, this open interval, which is nice. What about outside that interval? Suppose someone gave you this initial value problem, so this differential equation, this initial data, and said, quick, tell me a at 3. Or, ask me, would you please tell me, solve this and tell me the value of a at 3. Well, you could take this and plug 3 in and get something that's defined, right? You plug in 3, you get 2 over 4 minus 9, perfectly defined, negative 2/5. Fine. Is that right? No. In fact, we don't know. Or you're not given enough data to tell you what happens out here at 3, right? Your solution is only good on this interval. And what happens is you jump across these places where the solution's undefined. Takes some discussion. But what's true in general is that you get solutions near initial data, and you have to be careful. If someone asks you for the value of your function far enough away, so outside of the interval, an interval where your solution really is a solution that contains the initial data, it's possible that you can decide what happens out here, but it's not likely. And you really would need to be given information about what happens out there. Okay. All right. I want to conclude by giving you a word problem that translates nicely into an interesting differential equation. Just so you can see where, even without big physics formulas or without, engineering formulas, how you could just be given some problem in terms of rates of change that give you initial value problems. So let's look at, I had some specific numbers I want to use. So what I want to do is, suppose I've got a mixing tank. Industries actually do this kind of thing. Maybe not with salt water like I'm going to do, but salt water is easy to talk about because everybody has a feel for what salt water is. So I've got some tank. Here's the tank, and I'm going to assume it contains 50 gallons of salt water. So initially, contains 50 gallons of salt water and I'm going to tell you how salty the water is. We're going to assume it contains a total of 10 pounds of salt. Initially contains 50 gallons of salt water and a total of 10 pounds of salt. So, I mean, the salt concentration, what we're saying is that the salt is dissolved in the water, and so the initial salt concentration, so this says the initial salt concentration is 10 pounds of salt per 50 gallons. And we're going to assume it's uniformly distributed throughout there. So we're going to assume this is constantly stirred, so well mixed, so that any salt that's in the tank is uniformly distributed throughout the tank. So we have 10 pounds of salt in 50 gallons, so we're assuming that the salt concentration is uniformly 1/5 of a pound of salt per gallon. Great. Where's the differential equation? Nowhere yet. Now we're going to have salt water coming in. So suppose salt water that has 1 pound of salt per gallon. So I've got salt water coming in. It contains 1 pound of salt per gallon. So it's much saltier than the water that was initially in there. 1 pound of salt per gallon, and let's assume it's coming in at 2 gallons per second. All right, so salt water that's saltier than what we start with is streaming into the tank at 1 pound of, at 2 gallons per second, and its salt concentration is 1 pound of salt per gallon. We're stirring constantly, and now we're draining out. We're going to remove salt water at 2 gallons per second so that the level of the tank stays constantly at 50 gallons. So clearly the salt concentration in the tank will go up, right? I mean, we're taking water out at the same rate we're putting it in, but the salt water we're putting in is saltier than what starts in there. So certainly the salt concentration should go up. Of course, since the number of gallons is remaining constant, that means the actual number of pounds, total pounds of salt should be going up. And this is our question. What is, we'll find as a function of time, so our time will be in seconds. How many pounds of salt are in the tank? So let A equal, so a function of t equal the number of pounds of salt in the tank at time t seconds. Find it. We want to find A. All right. All right. The reason this comes out to be a differential equation, you've got rates of change. You're told the rate of change of, well, this information combined with this information, this tells you how many pounds of salt are coming in per gallon. This tells you how many gallons are coming in per second. If you multiply them, you'll get how many pounds of salt are coming in per second. So you're told something about the rate of change of the pounds of salt in the tank. So this is information about dA dt, right? It's the rate of change. You're also removing some pounds of salt from the tank. And you're told something about its rate, although it's a little less clear what we're told here. So anyway, this is a problem about rates of change, we're also given some initial data. We know A at time 0. A is the number of pounds of salt in the tank at time t. At time 0, we know there are 10 pounds of salt. So the initial data, we're going to get an initial value problem. The initial data, A at 0 equals 10. I'm going to drop the units. We're in pounds and seconds. But A at time 0, 10 pounds. All right. This problem might look hard to get started on. And yet, if you write enough words, it's actually easy. So what should you write? Well, and you shouldn't memorize something like this. It's just, you should remember how to think about it and how to break it down, but you shouldn't memorize the formula that we're going to get. So if you write enough words, hopefully it seems easy. You write the rate of change of salt in tank. All right, yeah, I'm leaving out the word the, and I'm writing the rate of change of salt when I mean pounds of salt, just to not write as much, but the rate of change of salt in the tank equals the rate salt enters minus the rate salt leaves. Hopefully, that seems obvious and doesn't take any memorization exactly. The fact that breaking it down like this is useful is something to remember, but the rate of change of salt in the tank, it's the rate salt enters minus the rate salt leaves. Oh, really? Okay. But the rate of change of pound, so this really means pounds of salt in the tank. That is dA dt. A is the number of pounds of salt in the tank. The rate of change, and I always mean with respect to time in this problem, the rate of change is dA dt. It's the rate salt enters. But the rate salt enters, this is the rate at which salt water enters. So you break this down. Actually, let me give myself some more room. But you break this down. This is the rate salt water enters times, well, the fraction of it that's salt, or the salt concentration. I'll just write the fraction that's salt. Salt concentration. So this would be this is the gallons per second. This is the pounds of salt per gallon. Okay, and the rate salt leaves. It's the rate at which salt water leaves times the fraction that's salt. So what do you get? All right, the rate of change of salt in the tank, dA dt, equals, all right, the rate salt water enters times the fraction that's salt. The rate salt water is entering, 2 gallons. Actually, maybe I'll write the units just so you can see how they end up. You get 2 gallons per second times the fraction that's salt, 1 pound, I won't write salt, but 1 pound per gallon. So that the gallons cancel and you get pounds of salt per second, as we should, minus the rate salt leaves. Well, salt is the rate at which salt leaves. That's the rate at which salt water leaves. That's 2 gallons per second. And then you get the interesting part. Here, what we have to do, the rate at which salt leaves, it's the rate at which salt water leaves times the fraction of that that's salt. So we need to multiply this by the concentration of the salt water that's leaving. But we don't know the concentration of the salt water that's leaving. We're stirring, so the salt water that's leaving has the same concentration as the salt water in the tank, but we don't know the concentration of the salt water in the tank. It's changing. We need to write an equation that's true at all times t that we care about, so we don't just put in the initial salt concentration. We need to put here whatever the concentration is at time t, but we don't know that. That's part of what we're trying to find. If we knew the concentration at time t, we just multiply times the 50 gallons and get how much salt we had. So what do we put there? Well, that's why you get an interesting differential equation, because it does involve the thing we're trying to find. the total salt concentration, the salt concentration of the stuff in the tank, which is the same as the salt concentration stuff that's leaving, we're stirring. So it's the total amount of salt in the tank divided by the total number of gallons of salt water in the tank. But the total amount of salt in the tank is the A that we're trying to find. And the total number of gallons of salt water in the tank at any time doesn't change. It's always this 50. So the concentration is whatever A is, it's divided by 50. Right? It's the total number of pounds of salt in the tank at time t divided by the 50 gallons. So this means that we get this initial condition and the differential equation, dA dt, equals 2 minus 2 over 50, so minus 1/25 A. And so we get this initial value problem. And the differential equation is interesting because A is the function we're trying to find, and it appears over there. We actually know how to solve this. When we did exponential functions, we actually covered enough that would tell us how to solve this initial value problem. But I'd rather not do that here because we'll deal with this equation, what's known as separable. We'll do that in a couple of sections. But I do want to say one more thing about this before we leave it. I was just trying to show you here how you get initial value problems from physical problems that aren't big physics problems. You just write enough words, you're given things about rates of change, and you get differential equations with some initial data. There is the question here of how can we use this initial data? This function, if we believe that we just kind of started this at time 0, we have a problem. Because to take the derivative, we need an open interval around each time. And if we don't believe this setup existed before time 0, then that means that here's the t-axis, here's 0. We're assuming things start here and go onward. But to know that we can take a derivative at time 0, we would need to know, in fact, that the situation existed at least a little farther back in time than 0. So what do we do in this case? In fact, you don't have to worry about this much, but let me say this one time in the introductory section, that either you assume that your physical setup existed for a little time before 0, or you assume that the solution that you get, right, you only assume that the differential equation is defined, that it holds for times greater than 0. So you don't include what happens at 0. But then how do you plug in initial data at 0? If this differential equation, if this derivative is only supposed to exist for times greater than 0, how do you get to plug in what happens at time 0 to give you information? And the answer to that is that we assume that you satisfy the that a solution to this satisfies the differential equation. We assume a solution satisfies the differential equation for t greater than 0 and exists and is continuous at time 0. So that you don't say that your solution has to satisfy the differential equation at time 0, but it has to satisfy it just, immediately after time 0, but that the function you're looking for should be continuous, and it should be defined at time 0. And then you'll find that, in fact, in problems like this, that it's as though you might as well have assumed the situation existed before time 0, because you'll get a solution to this that's continuous and defined at 0, and then you plug in at time 0, you have this, and it gives you a particular solution to the initial value problem instead of giving you a general solution. So the point of this is that things work out if either you make this extra physical assumption that you backed up a little in time or in your independent variable, or you assume you're looking for continuous solutions even when you hit points where the derivative might not be defined.